Welcome back, Physics 30. This is part 3 of the speed and velocity section. It corresponds to pages 71 to 79 of your duotang. And here we're going to look at instantaneous speed and instantaneous velocity. So far we've been looking at speed and velocity, average speed and velocity. Now we're looking at instantaneous speed and velocity and seeing how that works. Constructed position versus time graph, or displacement versus time. Analyze position versus time graphs, etc., to determine average velocity and instantaneous, as we did previously. So first of all, instantaneous speed is simply speed at a certain instant of time. So if you're traveling along the Trans-Canada Highway, look at your speedometer, 110 kilometers per hour, that is instantaneous speed. Instantaneous velocity is the same thing, except, hey, we have a direction this time. If you're traveling along, if you're going east towards Manitoba, you'd be going 110 kilometers per hour east. To describe a case in which two objects would have the same instantaneous speed, yet their instantaneous velocities are different. So you can see there, of course, if the magnitude is the same, the size, 110 kilometers per hour, is equivalent. That's equivalent instantaneous speeds. But if we have a direction component on there, one being north, the other one being south, they'd have different instantaneous velocities, and yet the speeds are the same. Okay, how is average, now this should be velocity, so make this little change in your question. How is it calculated between the 2 points in a distance time graph or displacement time graph? We've looked at this already. It's the slope joining the 2 points, so we looked at that earlier. Now what happens if the 2 points approach each other? Now if you look at your duotang, pages 73 to 74, it kind of goes into more detail about this. The speed approaches a constant value, and this leads to the idea of a tangent line. So put a star beside this. What we're really doing is we're magnifying the slope at a particular point on a graph. So for example, if I was looking at this region right here, I can see that the slope is kind of up like this, kind of pointing to the 2 o'clock position. So if I was to figure out the slope at this point here, I could see that it's kind of angling this way. That's what I'm getting at when I mean magnify the slope. So back in the duotang, the examples are a lot neater there, 73 to 74, you may want to look there. Just looking at a couple of examples here, if I look at this green curve here, and if I wanted to find out the slope at this particular point, I just don't simply take the distance over time there. It has to be 2 points, and to do that you need to make a line that goes right through that point only, which is kind of magnifying the slope at that point. So you can see this little black line here is kind of giving us an idea of what the slope would be in this little section, and if I extend that line using a ruler, I could pick any 2 points on that line, and that would give me the slope of that line, which is really a magnified slope for that area. This green graph, if I'm looking at this time period, I kind of make it a little bit larger with this black line that you see there. Take a ruler, increase it to magnify that slope. And then lastly, this funky curve here, if I wanted this time period to figure out the slope there, I can see that this is kind of the angle, and it's okay if I cross over the graph here because I'm only concerned about what does the slope look like at that particular point. Okay, so once again, if you're having trouble understanding this, go back to page 72 to 73 in that duotang. It'll illustrate a little bit better. But we'll see through a series of examples here. So state how the instantaneous speed is determined from a graph. So really what we're doing there is when we have a curve, and if we kind of figure what does the slope look like at that point, by taking our ruler, touching only that line and kind of seeing what the slope would be, what we're really doing is figuring out the slope of that tangent line. Tangent line meaning that it only hits the graph at that one point there and is magnifying the slope there. So then once I have that line, I can pick any 2 points on there, pick ones that match up nicely, d2 minus d1 over t2 minus t1. Okay? Now next I have a data table here. I'd like you to plot a graph. So there is graph paper in the room. Position versus time. So time is on the x-axis, position is on the y-axis. So pause the video right now, plot that graph, come and see me if you need help with the scale, and then we'll move on from there. Okay, if you had time to plot that graph, it should look something similar to this, except with all of the writing on it, etc. So you likely have a nice smooth curve that looks something like this, what I have illustrated here in blue. Okay, and we'll need that for the rest of this assignment. So position time graph here, nice curve. Okay, so the next question here, if we're using that graph, now I just drew a little miniature version over here so I wouldn't have to flip back. What is the average velocity for the first 5 seconds? Show how you determine this on the graph. So the first 5 seconds, 0, 0, and 5, comma. Now I think it's 5:13. Even on the data table, you'll see at a time of 5, it's a position of 13. So this is where our average velocity measurements come into play. So 0, 0, 5, comma 13. So really what we're doing is we're figuring out the slope of this purple dotted line here. 0, 0, 5, comma 13. So 13 minus 0, or 5 minus 0, we get plus 2.6 meters per second. Okay? And then lastly here, number 6, what is the average velocity from 2 to 13? So looking there from 2 to 13, so from 2, and then 13 is way over here, I believe. So we're actually figuring out the slope of this green dotted line. So if you look at your graph and get the two measurements there and figure it out, it should work out to be around plus 1 meter per second. Okay, it's 2 seconds of 13. You can even get that from here. At the 2 second mark, we're at 3 meters. At 13, we were at 14. So use that in the equation and you'll get your measurement there. Okay, so I didn't scroll the work here, so make sure you work through it and see what you get. Before we get into the instantaneous measurements, let's just do this one question and it'll be the end of this part 1 segment. At what time is velocity 0? How can you tell? So if we take a look at this curve, and I have this ruler here to kind of help out a little bit. So if we look here at the top, so we're increasing, increasing, increasing. Over here we are angled kind of like, at this point here we're angled very similar to that. And then as we approach the top, especially at the very top here, if I was to magnify what the slope of that point up there would look like, it would look very similar to a horizontal line. So that, and of course the slope of a horizontal line is 0. So position over time, velocity, that would be 0. So right at this point here, which represents the top of that curve, would be a slope of 0, which would indicate 0 velocity. So around 8.0 seconds, since the tangent line would have no slope. Okay, we'll stop there. We'll have part B in the next segment for this section D3 booklet.